formate issues on silica supported copper catalyst by Rochester and Go, which will be presented by Rochester.
Thank you very much. Could I have the first slide, please? This paper is with Graham Miller, who's now working in Auckland, New Zealand, and Ken Waugh, who works for ICI Limited, and we're grateful to ICI for supporting our work. I listened with great interest to the paper this morning by Professor Kahneman and to the comments afterwards. I hope that some of the stuff that I'm going to present will answer some of the questions that were asked then, although I suspect it will also generate even more questions than I managed to answer. We set out on this work concerned with the proximity of copper to zinc in zinc oxide in the working catalyst. Were there synergistic effects between the two? Was the copper in the copper naught or copper plus oxidation state? Was the spillover from copper onto the zinc oxide? Was the spillover from zinc oxide onto copper? Slide, please. And of course, we were also interested in the possible involvement of formate species in the reaction as intermediate. Was the formate on the zinc oxide? Was the formate on the copper? Or following Professor Nersinger's point this morning, was the formate bridged between the zinc oxide and the copper? And this is the type of intermediate which has been proposed before, and of course zinc oxide is reckoned to store hydrogen, so that there might be some synergistic effect between the two. Next slide, please. In order to study this, we thought we'd make things as simple as possible and get shot of the alumina component of the catalyst. We wanted just to look at copper, and we thought, well, silica's inert as you can get as a support, so that we'll look at 5% copper on silica to try and find out as much as we can about the copper. And you will notice that what we did was start with copper acetate. We gave it a calcination in oxygen at 350 degrees, and then this was reduced in hydrogen at 350 degrees centigrade. We got quite a good average copper surface area, and then when we wanted to add zinc, we added it with co-impregnation with zinc acetate, and the work that I'm going to, I hope I have time to present on zinc, will be 29 mole percent zinc compared with the copper content, 29 mole percent zinc. The next slide, the first question we asked, and Professor Kahneman answered the same question, is have we got copper naught or copper plus in the reduced catalyst? So we used CO as a probe molecule to try and gain information about this. The first slide shows CO on the freshly calcined catalyst, and you see we've got a band here at 2125 characteristic of CO bonded to copper 2 plus sites, and then there's another band higher up which is CO bonded to Cu2 plus sites, which are there having replaced hydrogen atoms on the SiOH part of the surface. And then there's a little gas phase band here. When we reduce the catalyst in hydrogen, then the dominant maximum was at 2098 centimeters to the -1, with a long tail towards 2000. If you compare this with data for single crystal copper surfaces, then this looks as if it's on high index planes of copper naught, and these bands probably on low index planes of copper naught. Notice that there is an initial band which stays there within here as a shoulder on copper plus sites, and I think that is important to Dr. Chadwick's point in the discussion afterwards. There's no doubt that in our catalyst we go under the vacuum conditions in our apparatus, have a little bit of copper plus residing in the surface after reduction. Because we were interested in whether copper naught or copper plus was active in the formation of formate, we also looked at catalyst samples which were given a reduction and then oxidized by treatment with N2O to produce copper plus. And when we put CO in those systems, two things happened very rapidly. One, we got an infrared band there and there, which is very similar to published infrared spectra of copper malachite, of the malachite type structure. So we believe that we've got a structure of this sort formed on the Cu plus surface with oxide ions already in the surface, And then there's an infrared band here, which is about halfway between the infrared band due to CO on copper naught and on copper 2+. But as a function of time, the CO has the ability to reduce the copper plus, generate CO2 in the gas phase, and begin to produce CO adsorbed on copper naught sites on the surface. So the CO can cause surface reduction. Because we were interested in formate species, next slide please, we adsorbed formic acid, and what happened when we adsorbed formic acid on the reduced catalyst is we got a band due to formic acid forming hydrogen bonds with silanol groups on the surface. We got bands due to formic acid ligated to copper sites in the surface, and we got bands due to the bidentate copper formate that we've already heard something about this morning. When we desorbed, we got rid of the weakly adsorbed material on the silica, but the ligated copper formic acid to copper and the copper formate, the bidentate copper formate, remained. When we adsorbed formic acid on copper silica which had been reoxidized with N2O, we did not see any of the ligated formic acid on the surface. We still got the hydrogen bonded material that pumped off, but we then got two bands due to formate, but in this case these two bands are different from the two bands I put down here. Particularly this band is in a higher spectral position, and we believe that this is a unidentate copper formate species. So the moral of this tale is if you've got a copper plus surface, you get a unidentate formate species. If you've got a copper naught species, you get a bidentate species. In terms of the addition of the formic acid to the surface, the ligated species actually appeared before the bidentate species. So the chances are that the ligated species is a precursor of the bidentate species on the copper naught surface. Next slide, please. We then took carbon dioxide. The rest of this talk is about CO2 hydrogen reactions. We took carbon dioxide on a reduced copper surface, and what we saw was two bands coming up, one due to carbonate species and one due to adsorbed CO on the surface. Now the point of this is that this looks like a simple disproportionation of carbon dioxide to adsorbed CO and carbonate. However, it's not quite as simple as that, because we found that this particular reaction was extremely sensitive to residual oxygen on the surface after the reduction had taken place. If we did not have any residual oxygen, then we didn't get any carbonate species. If we did have residual oxygen, and the more of it we had, the more carbonate species we got, and the more adsorbed CO we got. So in this particular process, it looks as if it is essential to have a little trace of residual oxygen on the surface, which almost acts as a catalyst for the reaction. Next slide, please. We then took, can you just lower that a little bit, please? We then took carbon dioxide hydrogen interactions with a reduced copper silica catalyst, and you will see that what we've got here is carbonate species. This is at 295K. One thing I should have said is that all these spectra were recorded at ambient temperature. We've done in situ studies at high pressure and high temperature, but everything I'm going to say here was recorded in a cell very similar to the one that Professor Knersinger described this morning. And although we have done some high temperature treatments, all the spectra are recorded at ambient temperature. And you'll notice what happens here is that with hydrogen present, we're reducing the surface a little bit to get some water formed, and then we're getting carbonate formed as well. There is no formate formed at all in this experiment. Next slide. But if we raise the temperature to 3A8 Kelvin and give it a burst at a high temperature and then record the spectrum again at ambient temperature, what we see is that the carbonate species undergoes a decrease in intensity. This is a different spectrum. As we raise the temperature, a big decrease showing that it's an unstable species and we get partial desorption of CO2. But then, as a function of time, at this temperature, we get loss of further carbonate and growth of formate species on the surface. And this is the bidentate formate. This is a surface which is largely copper north. We've got the characteristic bands here of bidentate copper formate. The next slide shows the correlation between the band intensities. Here's the desorption of some SiO2 from the surface, giving a decrease in the amount of carbonate. But then there's growth of formate, and the carbonate continues to decrease. What we believe is happening here is CO2 is reacting with the surface to generate more carbonate, but this is immediately changing slowly into formate species. So we are getting formate as the active species, or as the species present in situ under high temperature conditions. Next slide, please. We then, can you lower this again, please? We then took CO2 hydrogen with a reoxidized surface, and again we've got carbonate and water formed, but you'll notice the carbonate doesn't start appearing until the hydrogen has partially reduced the surface. That is, to generate this carbonate species, although we need copper plus in the surface and O2 minus to generate the species to catalyze its formation, we believe that this carbonate species is associated with what were copper north sites, and we have to generate some copper north sites by hydrogen reduction in the system before the carbonate will form. Next slide, please. If we now take this at high temperature, that is, we now warm it up, do the same experiment as we did with the reduced surface, then again these are different spectra. There is initially an enormous increase in the amount of carbonates present in the spectrum. This is a surface which is largely now oxidized to a copper plus species with oxide ions in the surface, and we've generated some copper north on the surface, but the CO2 at the high temperature generates a lot of carbonate almost instantaneously, but then this slowly goes as a function of time, and formate replaces it. So again, formate is the species which is present under high temperature conditions. And if we look at the correlation, the next slide, of the loss of carbonate and the growth of formate, here's the sudden formation of carbonate as we raise the temperature, and then the slow replacement of formate by carbonate. So this may suggest that carbonate is a precursor of formate on the surface. Next slide, please. We now thought, using the principle of the microscopic reversibility again that was mentioned this morning, we'd take some species which were further down the catalytic line to methanol. We put formaldehyde on the surface. If we put this on silica alone, then we get formaldehyde, the F's are just hydrogen bond into silanol groups, and we get polymerization of the formaldehyde, the P's. If we do it on a reduced copper silica surface at 295, then we get the same species formed. We get rather more of the polymer, that is, the copper seems to catalyze that, but the important thing here is that we get the bidentate copper formate again. So formaldehyde gives bidentate copper formate on a reduced copper surface. If we do the same experiment with methanol, next slide, then what we've done here is treated the surface with methanol at 25 degrees centigrade and generated a copper methoxy species. We've then raised the temperature to 393, and we've looked at different spectra. You can see these are SiOMe groups which are generated when you heat methanol on silica, but here is the copper methoxy species disappearing. This is on a reduced surface, and you will notice that we're getting the bidentate formate appearing in its place on the copper. So the methoxy is decomposing into the formate at the elevated temperature. If we do this on an oxidized surface, then we get rather more methoxy species formed here. They decompose. We get a unidentate copper formate and a bidentate copper formate, and the unidentate formate is formed first. So we believe CO2 may be going to carbonate, maybe to a unidentate formate via the ligated species to a bidentate formate. The next slide I think shows this sort of idea. We believe oxygen is essential. That is, you need copper plus on the surface to generate this species, but this species requires copper naught site for adsorption, a sort of symmetrical carbonate, that it then goes to formate and then goes via this mechanism, which is partly in the literature, through to methanol. So copper plus and copper naught, we believe, are both essential. Now, if I've got time, I can go on to the second part of my story, the next slide. We were interested now in zinc oxide. The first thing we did was put carbon monoxide on this. And the point here is that the CO spectrum is of exactly the same form as it was when there was no zinc oxide present. There's only a reduction in the intensity of all the bands. There's a lower surface area. We believe if you can lift this a bit, one explanation of this, and I'm not pushing this strongly, I'm just provoking argument in the discussion, that there might be zinc oxide over the surface of the copper, and this is providing a lot of close sites between zinc oxide and copper at the junctions, which I shall return to in a minute. Next slide, please. If we put carbon dioxide on zinc oxide alone, we get bands due to bicarbonate species. We heard about those in the first lecture this morning on another surface. This is in agreement with work by Lavalley at Caen, so that is the sort of result that we would expect. Next slide, please. If we put it on a reduced copper zinc oxide surface, then we do get an additional band, which we think is a CO2 minus species. We think that when copper is present, the hydrogen dissociation removes oxygen from the zinc oxide surface, provides anionic vacancies which CO2 can go into. We don't think that's particularly important to the catalysis, I might say. The next slide, please, shows that if we take CO2 and hydrogen with zinc oxide alone, there's no difference from CO2 alone. The spectrum is essentially the same. The next slide shows now if we rise the temperature, we get a little bit of a zinc formate form. So just a little bit of zinc formate. The bicarbonate is still there, a little bit of zinc formate. Next slide. We've now got, if you could lower this, we've now got copper in there. And again, with the zinc oxide, we've got bicarbonate formed, and we get a little bit of reduction of the copper surface with CO2 hydrogen at 295, and we believe this band is due to a bit of water which is formed by reduction. If we now take the next slide, which is at the elevated temperature, that is, we've now warmed it up, then immediately you can see that we start getting formate species. There's copper formate. Here's the original spectrum with the bicarbonate and a bit of water. The minute we raise the temperature, we get copper formate formed and we get zinc formate formed. And notice that there's considerably more zinc formate formed than we get with the zinc oxide silica alone. That is, the presence of the copper generates considerably more zinc formate than we would get if there was no copper there. Another point, which is not made in this slide and may be controversial, is we've done some other experiments with formic acid adsorption alone, and we believe that the bands we get when copper and zinc oxide are both present are in a slightly different position from the bidentate formate on copper or from the formate on zinc oxide alone, and also by TPD and TPRS experiments we've shown that the desorption characteristics are different. And going along again with something that Professor Nersinger said this morning, we believe that there's a possibility that this formate species may not be on the zinc oxide, but may actually be bridged across a copper site and a zinc site. If I can take the next slide, please. This shows what happens if you put methanol on. Then this is on zinc oxide alone. These are SiOMe bands, and we get zinc OMe. If you take the next slide, and this is the important one, we put methanol on copper zinc oxide silica at 393K. you see we get copper methoxide and zinc methoxide. Now this methanol was put on an ambient temperature to generate the methoxy species. There's two bands due to SiOMe which are irrelevant to us. They are spectators. But you'll notice that when we raise the temperature to 393, the copper methoxy species decreases in intensity, but it is mainly zinc formate species, or if you prefer this bridged formate species, which is growing in intensity. So it looks as if there is some synergy between the copper and the zinc, that we're losing a species on the copper and gaining a species which is at least interacting in part with the zinc on the surface. And if you do it on an oxidized surface, you get now more copper methoxy species in this experiment, and you get more zinc or bridged zinc to copper formate species generating as a result of that. So there's no doubt in our mind that there is some synergy between the copper and the zinc oxide surface, and this may involve either spillover or it may involve actually bridging sites at the interface between the copper and zinc oxide on the surface. My final slide just shows some of the believed roles of zinc oxide in this. And you see that among these, creation of unique active sites at the copper-zinc oxide interface. I throw that out as an idea. I don't pretend we've proved it at all, but it is something worth discussing. We don't believe that the zinc oxide particularly is affecting the copper in an electronic sense in our catalyst, because the CO adsorption spectrum was exactly the same on the copper, whether the zinc oxide was there or not. But we believe that there is going to be some bifunctional reaction, that is, the overall catalysis certainly believes the involves the copper and the zinc oxide. And in fact we have done experiments, as I say, with TPD and TPRS which support these conclusions, and in fact show that there are spillover effects involving the hydrogen as well. Thank you very much for your attention.
Very much. Please question.
Professor Rochester presented a fantastic amount of data, which I think would be enough for a whole session. I'm a little bit lost now, but I would like to concentrate on the behavior of the copper silica, and I would like to compare the behavior of copper with that of the platinum metal. So when we studied about 10 years ago the H2CO2 and H2CO interaction on supported platinum metal, we observed the formation of carbonate and the formate. But finally we came to the conclusion both species locate on the support, because in the case of the silica supported metal, we did not find any indication of the presence of formate and carbonate. But I think that the situation here is different, because you detect carbonate, formate, even in the case of silica supported copper. So I think the copper can locate, can accept both species. But my question is that did you not determine the concentration of the carbonate and formate? Because my problem is there enough space for the absorption of these species on the copper?
I think the answer to that question is that we did not do that quantitatively. We did not get any estimation from the infrared data on the amount of carbonate or bicarbonate present in our systems. So I guess my answer is an unsatisfactory one, really, but I take the point that you make, and it's clearly a very, very important point.
A short question, Professor Rochester. Have you investigated the absorption of methanol, carbon dioxide, formaldehyde on pure silica?
Yes, we've done all that. We've done all those things, not only in connection with this work, but we've done it in connection with work on rhodium catalysts, and we've done all that from ambient temperature and pressures below an atmosphere up to 50 atmospheres and temperatures at 280 degrees centigrade. And none of what we see is anything to do with the silica at all. Under conditions when there is no copper or zinc oxide there, I said under some circumstances, of course, we do get spillover onto the silica surface, particularly in our rhodium systems we get that, spillover onto the silica surface, following catalysis over the metal component. But we have done all that as background. And we've always done it on silica, which has been subjected to the calcination and the reduction process, which we normally do for the supported metals.
In some of the places which you describe as spillover, my TPD measurements in some of these systems indicate that there is a really strong reabsorption phenomena, so one tends, in fact, to do no kinetics at all, just measure thermodynamic properties. Isn't it possible, for instance, that you could get, let's say, reversible desorption of methanol and its reabsorption onto the zinc oxide in those particular experiments you described as spillover?
You mean it's transporting through the gas phase?
Well,
effectively. Yeah. I mean, if you believe that it's a bridged species across the copper and the zinc, then of course that is not happening. And the desorption characteristics of the species we got are quite different from the desorption characteristics which we get, say, for formic acid on zinc oxide alone or on copper alone. And in that particular situation, then I guess you wouldn't refer to it as spillover anyway, except that it probably starts off life ligating to the copper and then goes on to the zinc, and so it's spillover in the sense that it's whirring around like a propeller and then bonds down. But again, I mean, I take your point. If you raise the temperature, you say, well, could there be some desorption and reabsorption? That is something which needs investigating, clearly. This is what I said at the start. I may answer some of the questions from earlier this afternoon, but I think I'm asking a lot of new questions, and I think a lot of the results that we've got are provocative, and I've deliberately been provocative, and I think there are experiments which are needed to test that particular point. But I will say one experiment we did. We took a disc on which we got copper and zinc oxide and silica, and I think we took a disc on which we got zinc oxide and silica alongside it. And we did the experiment, and we didn't find anything on the zinc oxide silica disc which had jumped across the gap. I think we did that experiment. I certainly hounded the student to do that experiment, and I seem to remember that he did it. And that he assured me that there was no jumping over, because we had thought of the particular thing that you're suggesting.
Yeah, but I mean, frequently people don't investigate that phenomenon, which is really quite easy. For instance, in temperature program desorption experiments, if there is desorption and reabsorption, and it can be within the pores, the temperature, the peak temperature is a function of the log of the campus mass, so it's very easy to tell. And in fact, from that shift, you can extract the heat and absorption.
We have seen that sort of effect in other experiments involving rhodium catalysts.
This is one professor that's whirling around like a propeller button. But I wanted to ask a bit about quantitation, because when you've got copper on silica, you've got an enormous surface area per gram of copper, something of the order of 136, I think you said in your case. Of course, you won't get anything like that area of copper on the zinc oxide. You'll have
70.
70, okay. Now, when you have your band, which you regard as the bridged band between the copper and the zinc, the quantity that you can get is going to be dependent upon the contact area between the copper and the zinc oxide. So it should be a relevant experiment to do, to compare the intensity of your bands, making assumptions about the extinction coefficients, with the particle size of the copper, in order to be able, I think, perhaps to provide a little more supporting evidence for the idea which, of course, many of us have, that the synergy is a close contact between the copper and the zinc oxide. But I think that if I might urge you to do some more quantitation in respect of systems which have been characterized with regard to the copper particle size.
I have been urged to quantify our results by Professor Stone and Professor Shirley-Moshe. I must go away and quantify my results. I have a new student starting in September, and the sort of experiments that we were going to do involves just this problem, trying to establish situations where we have different amounts of contact between the copper and the zinc oxide to see whether or not we can try and confirm some of these ideas which we're putting forward.
One more. The formate located on zinc oxide surface is remarkably activated by the co-adsorbed hydrogen. But the formate is not reactive to the methanol or methyl, but to only decomposition to hydrogen, water and carbon monoxide in the co-adsorbed hydrogen. So my question is related to the question to Dr. So I want to know the coverage of adsorbed hydrogen on zinc oxide surface.
Well, I think that's another bit of quantification which we don't probably know the answer to. So I'm getting the same message from three members of the audience now. That is very, very useful.
Thank you very much.